Good afternoon, everyone. I am Roshni. I am studying in Srinivas Ramanujan Institute of Technology. I am from CRCE section. Today, I am going to present a video presentation on fast multiplication methods by using a Booth's algorithm. Everyone gets a doubt that why fast multiplication matters in digital logic systems, because there are so many things: fundamental operations, performance bottleneck, algorithms, and advantages. Multiplication is the cornerstone of a computer algorithms, digital signal processing, and embedded system computations. Every modern processor relies on efficient multiplication to performance. Performance bottleneck. This means that how it performs the conventional binary multiplication that requires a numerous addition and so many shift operation to create a significant delays in a computational workflows and limiting overall system speeds. And algorithm advantage. This is the thing where Booth's algorithm dramatically reduces the most number of operations needed. That means it accelerates multiplication processes and it enables faster, it more efficient hardware implementations. This optimization is essential for modern processors, DSP chips, and embedded systems where computational efficiency directly impacts performance, power consumption, and cost effectiveness in digital applications. Why Booth's algorithm? In the history, let's see the historical foundation about this. This was developed by Andrew de Booth in 1950. So that is why it came as a Booth's algorithm. The scientist's name is a Booth, and this revolutionary algorithm transformed how computers handles signed binary multiplication. Unlike conventional methods, Booth's approaches works seamlessly with two's complement representation, treating positives and negative numbers with equal efficiency. What's the core innovation between this? The algorithm examines consecutive bit pairs in the multiplier to make intelligent decisions, and the multiplicand subtracted to perform no operations at all. This strategic approach minimizes the number of partial products by efficiently encoding runs of consecutive ones and zeros. The elegant solution handles both positive and negative operands uniformly. They both handles equally, making it deal for processors that use two's complement arithmetic throughout the design. The key advantage from this Booth's algorithm means it reduces the average multiplication time by approximately 50% compared to traditional shift and add methods. Booth algorithm rules for bit pairs qn, qn plus 1. There are patterns, like let's see the patterns. Pattern 10, action. We have to subtract multiplication from partial product. This indicates the end of a string of ones requiring subtraction to correct the accumulated sum. Next, pattern 01. This adds multiplication to partial product. This marks the beginning of a string of ones initiating the addition processes. Pattern 00 or pattern 11. The no addition or subtraction. The action here is there is no addition or subtraction. These patterns indicates continuation of the same bit value, requiring only a shift operation. After each performance, arithmetic right shift on the combined resistor systems AC plus QR plus QN plus 1, which preserves the sign bit to maintain a proper 2's complement, which represents throughout the process. Let's see the step-by-step example. Let's multiply minus 5 and minus 7, which is a 4-bit. First, the initial step is the multiplicand is a minus 5. We have to convert that into 2's complement. We know how to do that. We know how to convert that into 2's complement, right? And the multiplier minus 7. And that is also we have to convert that into 2's complement. That becomes 1001. And we have to initialize AC equals to all zeros and QR equals to 1001 and Qn plus 1 equals to 0. SC equals to 4. First iteration, we have to first iterate. Qn plus 1 equals to 10. We have to subtract the things and the continue process. We have to first we have to repeat the remaining iterations, checking bit pairs, apply, add or subtract or shift operations as determined, decrement sequence counter after each cycle. The final result SC equals to 0. Fundament product appears in AC plus QR, which results a plus 35. See, minus into minus is plus. We know the verification, so we can do easily. Let's see the visible flow chart of a Booth's algorithm. First, we have to initialize the phase. Then we have to examine the bits. Then we have to take a decision on operations and we have to control the iterations. First, let's see the first step, initialization phase. Set up resistors AC, accumulator, QR, multiplier resistor, QN plus 1 and SC. SC means sequence counter. We have to set these things with the initial values. Then we have to examine the bit values. Check the current bit pair
Power off.
Qn and Qn plus 1 to determine the required operation based on a boot's encoding rules. And we have to execute, add, subtract or no operation based on the patterns. And we have to control the iteration and then output the final product from combined things. And the hardware implementations overviews. Let's see these things. Essential components: AC resistor, QR resistor, flip-flops, adder or subtractor, then control logic. AC resistor. It accumulates the partial products during multiplication. In control logics, the control or unit or the entire process. This manages the sequence counter. It interprets bit pairs and coordinating the arithmetic right shift operations that preserve signed bits throughout the computation. This is effective design and it's a time control things. Digital logic gate representation. This is the main important thing. First, it processes the input, then it decodes the control logic, then arithmetic right shifts, then output register. First, input processing means multiplicand feeds into an adder or subtractor unit, while the multiplier loads into the QR register alongside the flip-flop. Controller logic decoding. It is a combinational logic circuits decode bit pairs. And arithmetic right shift. Multipliers and flip-flops implement the shift circuit, preserving signed bits while moving data through the resistor chains. And the output resistor. Final product accumulates in the combined AC and QR resistors. Let's see the practice problem. Multiply 6 into minus 3 using Booth's algorithm. We have to apply this algorithm to solve this multiplication problem by using the step-by-step. First, given values multiplicand is 6. We have to convert that into 4-bit. It's a 0110. It becomes multiplier Q, which is minus 3. That becomes 1101. First, we have to initialize the resistors. AC equals to, we all know that it's 0000. QR equals to 1101. Qn plus 1 is 0. SC equals to 4. Now, our task is to follow the Booth's methodology. First, we have to check Qn plus 1 bit pairs. Then we have to add or subtract or no operations if there is nothing is required. Then arithmetic right shift, then decrement SC and repeat. Yeah, these are the solution steps. Iteration, first we have to iterate, then right shift, then final result. 6 into minus 3 is minus 18. The expected results, the final product should appear as a negative number in 2's complement form. The summary and takeaways. This algorithm's efficiency, the signed number handling, hardware applications, key understanding, outcomes. Understanding both algorithms is a fundamental for computer architecture design. This technique bridges theoretical computer science with the practical hardware implementations. Mastery of this algorithm provides insights into DSP design and embedded system optimization. Regular practice with examples and hardware diagrams depends computational thinking skills. Thank you everyone. Thank you ma'am.